Okay, so we just solved this finite square well problem. We got the general solutions in each of these three regions, and all we need to do now is use the boundary conditions at each wall to find these, to relate these coefficients. And so again, those boundary conditions are that the wave function should be continuous and that the derivative of the wave function should be continuous at each of these walls. And if you just start out and try and do that using these expressions, you're going to have a very bad time. So actually, the easiest thing to do is to break this down into two simpler problems. So what we're going to do is, instead of having this form for phi2, we're going to look for solutions that are odd or even. And this is another one of those things that seems kind of random the first time you come across it, but actually it makes a lot of sense because our potential is symmetric about 0 here. So if the potential is symmetric, then we would expect that the modulus squared of the wave function is also symmetric, because the modulus squared of the wave function, it tells you something physical. It tells you how likely the particle is to be at a certain point. And if the potential is symmetric, then the particle should be just as likely to be on one side of the well as it should be on the other. So we get that constraint that the modulus squared of the wave function should be even or symmetric. And if the modulus squared of the wave function is symmetric, then that tells us that the wave function can be either odd or even, because the modulus squared of an even function is even, and the modulus squared of an odd function is even. So what I'm going to do is, rather than choosing this form for phi2, is I'm just going to look at solutions where phi2 is even. So I'm going to choose cosine of k prime x, because cosine is even. And so we're just going to solve this problem, and so we'll have to solve, two problems. We'll solve this problem, and that will give us all of the even solutions to our problem. It'll tell us all of the even eigenfunctions. And then we'll have to go back and instead choose sine and solve that problem, and that will tell us all of the odd solutions to our problem. And so the total eigenfunctions will be both, all of the even and odd solutions. So let's just work out the even solutions for now. So we're going to use our boundary conditions on phi and its derivative. So I've written the derivative for each of my three regions here. And we'll just want, so the first condition is that phi1 and phi2, so phi has to be continuous at the left wall at minus L over 2, so we should have that phi1 of minus L over 2 is equal to phi2 of minus L over 2. And that leads us to this equation. And the derivative of phi1 at minus L over 2 and the derivative of phi2 at minus L over 2 should be the same, so that our derivative is continuous, and that leads us to this equation. And then we'll have two more equations that are just the same thing, only applied at the right wall. So at L over 2, we need phi2 to equal phi3 and phi2 prime to equal phi3 prime. So we'll have these four equations in total. And from these, you can read off pretty immediately that, well, first off, A is clearly equal to C. So that's easy. And then we'll have another equation. So we have two equations for A here. So I can set these two equal to each other, and I get this equation. And since A is equal to C, that this doesn't give us anything new. So I just have this. And if you simplify this a bit, you come to this expression. And so this is just like before when we did the infinite square well. So we didn't find out what all of our coefficients were, because we should have one undetermined coefficient that is going to be, it's decided by normalization of the wave function. Instead, what it tells us is it gives us a constraint on k and k prime, which are, and hence the energy. So again, k and k prime are just some function of the energy. And so this is an equation that is analogous to the equation we got for the infinite square well, where we found that k had to be n pi over L, where n could be any integer. And so that was a nice analytic expression, and we could just easily write down the allowed eigenenergies for our states, for the eigenstates. But here, this is not an expression you can just solve for E. You would have to do it either numerically or graphically and find all of the values of E that satisfy this equation. And those would be your eigenvalues. So if you do that, then you can write down your solutions. So the even solutions would look like this. And here I've just related, B. I can solve for B in terms of A from this equation. So I've done that here. And again, we have A is undetermined because we'd have to find it from normalization, which I'm too lazy to do right now. And so these are all of our even solutions. So another difference that we have from the infinite square well is for the infinite square well, equation that we had, that k could be n pi over L, n could be any integer. So there were an infinite number of solutions to that equation. So we had an infinite number of eigenenergies and hence an infinite number of eigenstates. But for this equation, there aren't an infinite number of solutions. So actually we can I've plotted it here. So remember, k goes as square root of absolute value of E, and k prime goes as square root of E plus V. So the approximate, I've plotted them both here, approximately. So ignoring this one for now, I'll talk about what this one is later. But so I have these two equations here. So this one's plotted in red, this one in green. And I want the solutions to, this equation will be when these two functions are equal to each other. So, didn't want to do that. So basically the solutions are where the red lines cross the green line. And one thing you have to remember is that E in our problem is negative. So we're looking at bound states. So we're only looking at states where E is less than 0. So we don't care about crossings that occur for E is greater than 0. So we don't care about these intersections. We want intersections to the left over here. And notice I've set my potential, I've set V naught to be 0. So and in that case, you can see there are no intersections. So there are no solutions because there's no well. So there can't be any bound states if there's no well. But you can watch as we increase the value of V. So if I have, I guess a pretty shallow well here, then you can notice that this thing moves. And so I have an intersection here. So I have an eigenvalue with eigenenergy minus 0.968. So I have one eigenstate for this, value of V. But you can notice as I increase V, you can see the lines getting closer. Here, I actually need to make this. If I make it 100, or here, we can watch it. So as we, make V deeper and deeper, we get more and more intersections. So we're getting more and more solutions the deeper we make our well. And obviously this makes sense if we made V infinite. If we just make V really big, to zoom out here. Okay, maybe I shouldn't have done that. Not so big. But the point is, as I make V very large, it should approach the infinite square well solution. So we should have an infinite number of solutions. And here you can see, basically, as you make V bigger, you get more and more intersections, and hence more and more eigenenergies, more solutions. So that's another key difference between this problem and, oh, I've screwed up here. Okay. And the infinite square wells. We don't have an infinite number of solutions. Another thing that's usually is pointed out, so again, this is for my even solutions. If V, you can ask the question, okay, how small does V have to be for there to be a bound state that exists? So for there to be just even one solution. So you can see if I make V really small, I always have this intersection over here. So there's always a solution. So what that's telling me, and even if I make it, 0.01, I still have It's just this intersection here. So the point is, no matter how shallow my well is, there is always one bound state, which is kind of interesting. You would think that if V was, if there's barely any dip in the potential, you would expect that, well, how can that well contain anything? But apparently, no matter how shallow you make the well, no matter how little you make V, there is always one bound state. So again, this was all for the even solutions. I can do the same thing. I'm not going to do it because it's literally the exact same process. I would just start back over from this point, and instead of choosing cosine as my solution, I would choose sine, and I would have the same kind of boundary conditions, and I would get different equations, and everything would work out kind of similarly, and I would get another different transcendental equation that I would have to solve for the eigenenergies for the odd solutions. And that's what I've got here. This is the other transcendental equation. So it goes as, instead of going as tangent of k prime, it goes as minus cotangent of k prime. So if I turn this one off and turn this one on, it's, we'll have a similar kind of thing. Okay, where is the... Oh, okay, just too far zoomed in. So again, you'll see that as I make V bigger and bigger, I'll have more and more solutions. Okay. No. Okay, wait. Hold on. All right, yeah, so it's a similar kind of thing. As I make V bigger, I get more and more solutions, more and more intersections. Only for the odd solutions, I don't have. Remember, for the even solutions, no matter how small V was, there was always an intersection. So there's always one bound state. But for the odd solutions, if V is too small, then you can see I don't get any intersection. So V has to be, at least, I don't know, something larger than a certain value for there to be a bound state that exists. So again, that's just telling us that as we take the limit of V going to be very small, there's only one bound state, which is that even state.